Good morning, everyone. And today we are going to talking about the lecture. And the last lecture we had talk about the variational methods, the original idea, and the variational problem and the boundary volume problems. And in section 2, we mainly talk about the relation between the variational problem and the solution to boundary volume problems. And in this section, we talk about three equations. And the first is the algebraic equation. And the second is the ordinary differential equation. And thirdly is the elliptical partial differential equations. And we have said that in three cases, we are constructed the functional J as this, and then the functional J's extreme point is just the solution of equation. And here, J has two important characters or properties. First is L is symmetric, and the second is L is positive definite. And this form you should take it in your mind. And in section 3, we give the Euler-Lagrange equations for fractional variational problems. And in this section, we give this form. Not work. And in section 3, we consider the function of the form as this. And this here is the left fractional derivative, and this is the right fractional derivative. And then a necessary condition for J have extreme for given function Y is Euler-Lagrange equation as this. And we had pointed out that this is very important. And firstly, we the derivative is about the left fractional derivative, and then here is the right fractional derivative. And here is first is about the right fractional derivative, and then is the left fractional derivative. And this form is interesting. And today we go on the lecture under the fourth part, fractional boundary volume problems via variational method. And there are three subsections. Under subsection 4.1, we will introduce some critical point theory, and maybe some of you are not familiar with this. and we will give some important concepts and results. And in 4.2, we will show you various fractional boundary volume problems. And there are so many boundary volume problems have been studied. And we will see if there are some boundary volume problems can be solved via variational method. And in section 3, and we will, by using our critical point theory, to give some existence results for FDVP. And also 3 subsection. And firstly, establish some fractional derivative space. And in mathematics, when we solve some problems, we are common, firstly, establish space. And then in this appropriate space, we will study if the problem considered has a corresponding structure. Here is a variational structure. And lastly, we will give the existence of weak solutions. Here, R is located in this interval. Firstly, we consider the critical point theory. Many boundary volume problems are equivalent to AU equal to 0, where A is max Banach space X to Banach space Y. For example, we consider U double prime plus FTU equal to 0, and equate the boundary conditions U0 equal to U1 equal to 0. This is the boundary volume problems. And by the use of the green function dts, and when t less than s, it is defined as t times 1 minus s, and in another case, it is defined as s times 1 minus t. And by the use of the green function, and we can define operate tu equal to dts minus f sus, and integrate about s from 0 to 1. And then the boundary volume problems equal to solve the boundary volume problems equal to find the fixed point of t. It is said that if u equal to tu, then u is the solution of boundary volume problems. And equivalently, if we set a equal to I minus t, then the boundary volume problems equal to AU equal to 0. And then we changed the boundary volume problems as this and this. And when the problem is variational, there exists a differentiable function of phi x to r such that a equal to phi prime. It is and there exists a functional phi, and this limitation denoted as AUV. And then equation 4.1 is equivalent to phi prime u equal to 0. It is phi prime u equal to 0 is meaning, and for every v belong to x, there is phi prime u v equal to 0. And phi prime u equal to 0, it is called u is the critical point of phi. And the volume of phi at critical point u is called the critical volume of phi. And then, according to the above arguments, we know that when we solve the equation AU equal to 0, as long as we find the function of phi such that phi prime u equal to 0, and the work be changed as how to construct the function of phi, and how to find the critical point of phi, and how to find the critical volume of phi. This is the problem. And suppose the phi has to be constructed. Then the main problem is how to find the critical point volume of phi, and which is the candidate. We consider this problem in two cases. And the first is if the function of phi is bounded from below. And you see, if the phi is bounded from below as this, and this bounded from below, then the infimum exists, and this volume is a natural candidate. And Eichmann variation principle implies, and there exists of a series un such that phi un tend to C and phi prime un tend to 0. And if un satisfies this condition, we call un either PS sequence at level C. The function of phi satisfies the so-called PSA condition if any PS sequence at level C has a convergent subsequence. And this is the PS condition. And in this, if phi has this structure bounded from below, and then the result, corresponding result, is if phi is bounded from below and satisfies the PSA condition at level C, then this volume is the critical volume of phi. And this is the first case. The second case is the function of phi has a mounting path structure. And what is the mounting path structure? And see, function of phi has a local, but not a global minimum at 0, and there exists positive R, and X2 belongs to this space, such that the normal of X2 greater than R, and this relation holds. This relation holds that 0 is a local minimum, not the global minimum. And when we consider the set gamma of paths joining 0 to X2, then this volume is also a natural candidate of the critical volume. And this expression is very abstract. And we can see this figure. And this pointer is 0, and this pointer is X2. And 0 is a local minimum. For example, U mean me stand at 0, and the surrounding is the mountain, and there is another component x2. It is lower, and then I will from this point to that point, and from this point and climbing the mountain and to this point, and then the problem is which path is the best one. Which path is the best one? And the first path, you can see there are many paths can go from 0 to x2. And so you must define which is the best. The best is how many. We can say, and if we choose the different paths, and the height of each path is different. For example, if you go from this to this, the height is here, and if you from this point goes through this point pass to here, and the height will be higher. Definitely, the lower you height, the less energy you spend. And so you see, and this volume, and given a path, and firstly you commute the height, the path height, and then you commute the infimum in our path, and just this volume is the critical volume of phi. This theorem called mountain path theorem or mountain path lemma, it is a very important result in nonlinear functional analysis. You will find that in first case, functional phi is bounded from below, and second case is phi has the mountain path structure. Now, this is very visualized and acceptable to us. But somebody will find the PS condition. Here phi satisfies the PS condition, and in second case, the PS condition also be required. And this condition is mainly to deal with the infinite dimensional problems. If we consider the problem in finite dimensional space, and this condition will not needed. Under the finite dimensional space and infinite dimensional space has a greater difference. And to feel about the difference, we will talk our story. It is come from David Hilbert. And Hilbert is a German mathematician. and he is the most influential and universal mathematics of the 19th and 20th century. He formulated the theory of Hilbert space, one of the foundations of functional analysis. And he also famous about his 23 problems. And these problems greatly influence many mathematics work. We will talk about so-called Hilbert hotel, this story. And some of you may know this story, and some of you may not know it. Hilbert's hotel, illustration, for example, this room has 30 seats. If we have 30 students here, then every seat be occupied. And then there has a newcomer, a new student, and definitely he will not find a spare seat for him because every seat has been occupied. But we imagine another case. If this room has infinite seats, this room has infinite seats, and every seat has been occupied, and then a newcomer. Then there is a newcomer, and can you give a seat for the newcomer? Taking it in your mind, every seat has been occupied. Can we find a spare seat for newcomer, new student? Yes, you can. How to find it? And you can give everybody a number and every seat a number. And firstly, student one, seat the student seat one, student two, and seat two. And then we let the student one to take seat two, and student two seat seat three, and student three to seat four, and the student n to seat n plus one. And go on and go on. Then you will find that everyone have seats, and the seat one is spare. And then the newcomer can sit this seat. Not just in this case. If they are, for example, they are 100 newcomer, can we find the seat for this man? Yes, you also can do it. Just later, student one seat 101, student two seat 102, and then the former 1, 2, 3 to 100 seats will be spare for the newcomer. And not limited in this. And if And this is the story about the Herbert Hotel. In fact, if they are infinite newcomer, you also have the method to find the seat for them. And from above story, you just remember that infinite dimension space has a great difference to finite dimensional space. And this is Eckland. We have the Eckland variation principle. It is his famous work. And he is Canada's chief scientist. And he has been to China, and he is the friend of Professor Leng Yiming. And this is ME280, and ME280 and Zhanbing gave the mountain pass lemma. This is a classical tool in the context of nonlinear analysis problem. And this is Paul Rabinovich. He is a professor at the University of Wisconsin Madison campus, and he works in the PDE and nonlinear analysis. He had awarded Booker Prize in 1998, and he was a member of the United States National Academy of Science in 1998. In 2008, I have seen Professor Rabinovich, and there is an international meeting, and I have asked him a question. In that time, I'm very interested in variational method, and I had asked him if three-pointer boundary volume programs has variational structure. And Rabinovich is a very nice man, and he spent 2 hours and 2 pages told me no. It is a pity to me because I think that problem has very structure, but Professor Rabinovich say not. Because my English is not good enough, so I miss the chance to have a talk of him. It's my dream, and someday I can say no to him, or not to him, to his answer. And now, 4.2, in this section, we give various fractional boundary volume problems. And firstly, we say fractional 2-point boundary volume problems. Here, R is between 1 and 2, and see this equation with these boundary volume conditions. And here, B is the standard Riemann-Leibniz reflection derivative. And this work is published at 2005. It is my work. And now this work has been cited more than 500 times. And this is the first work about the fractional boundary volume problem. And for alpha between 3 and 4, we consider this function. Because the alpha is in this interval, so there are 4 boundary conditions needed. And this is so-called 3-point boundary value problems. And R is also in between 1 and 2, and the boundary conditions involve point 0, point eta, and 1, and so it is 3-point boundary value problems. And the constant beta and E satisfies this relation. And this is the integral boundary conditions, and alpha greater than 2, and you will find that the boundary conditions involve integral, so it's called integral boundary conditions, boundary value problems. And here, the fractional derivative is capital fractional derivative. And this problem is also called 3-point boundary value problems because 0, 1, eta, 3-point. Here, the constant theta and E, 8 satisfies this equality. And in this condition, we call this problem is at resonance. And it means when f equal to 0, the corresponding linear problem has an infinite solution. So this problem is called a resonance problem. And this is called infinite interval boundary value problems. And you will find that here T is located in this infinite interval. And the boundary conditions also about the infinite point. And this problem is impulsive boundary value problems. You will find that despite the function and the boundary value conditions, there are also this. This is the bump, and in this point Tk, and there is a bump about the value of u or the value of u prime with derivative. And this is called the IVP for fractional functional inclusions with a finite delay. And this belong to is inclusions. And when t belongs to this interval, y is given as phi, and it's y, yt, yt theta equal to yt plus theta, and this is delay. And so there are many boundary value problems has been studied by using the nonlinear functional tools. And our problem is, can we solve above problems via variation method? Another thing is above problems has variational structure, and no one answers this problem. However, some mathematics has studied the following two types of boundary value problems. They can, these problems can be solved by using use of the critical point theory. The first BVP is as this. You see, and U first the left fractional derivative of order alpha, and then the right fractional derivative of the alpha. And this denotes RR LFD and LR LFD. R is between 0 and 1. And we can find that especially when alpha equal to 1, then this composition can be changed and the second derivative. And this problem is very common and has widely studied by mathematics. Another FBVP can be studied where the critical pointer theory is as this. And it is also a composition. You will find that the order of this equation, is 1 minus beta and 1. So the order of this equation is 2 minus beta. And beta between 0 and 1. And especially when beta equal to 0, then the order of here is 2, and then we get the common problem as this. And we will focus on our arguments either this problem 4.3. And firstly, we construct the fractional derivative space. Firstly, construct the space, and then consider the structure, and thirdly, consider the solvability. And firstly, denoted by C0 infinity is the solvable space. And this 0 means H0 equal to Ht equal to 0. And now we can give the definition of fractional derivative space. E0RP is defined by the closure of this space with respect to this norm. And this is U, and this is U's fractional derivative. And here are another 3 norms. U, RP, the interval is 0, t, and this is U, capital RP, and this is U, infinity norm. And in the following, there will be many theorems. Don't worry about that, because your matter is not mathematics. So you just you just know about the structure. The details is not the problem. Theorem 4.3, and if R is as this, P as this, then the fractional derivative space is a reflexive and separable Banach space. You just to know, and this space, we construct a space is a good space, has good properties. Under 4.4, R and P and this, for U, belong to this space. If R greater than 1 over P, we have this formula. And this minus R means this is integral operator. And we know that integral operator is not the left inverse of derivative operator, generally speaking. But in this space, the formula holds. Because we not consider all function u, but the special u. Under 4.5, this theorem said that if R and P satisfies these relations, one of these relations, then we have some estimation about the different norms, and this norm and this norm, and the infinite norm and the RP norm, the relation, the estimation. Under 4.6, if R satisfies this condition, and then UK converges weakly to U, then UK can converge strongly to U. And then we give the variational structure. Under if P, R, and L satisfies these conditions, here, and P and Q satisfies this equality, then the functional phi defined as this. This is important. The functional phi defined as this integral, by this integral, then phi is a continuous differentiable on the fractional function space. And the derivative of phi can be derived as this. Under theorem 4.8, say that if L is defined as this form, and satisfies this condition, for alpha between half and 1, then U is the solution of phi prime U equal to 0. It is said that U is the critical pointer of functional U, then U is the weak solution of boundary volume problem 4.3. So-called weak solution means U satisfies this this is equality. And this theorem tells us about the relation between the critical pointer of phi and the weak solution of boundary volume problem 4.3. And then we come to the existence of weak solution with R between this interval. Firstly, if F satisfies these conditions, and capital F satisfies this this condition, and then boundary volume problem has at least one weak solution which minimizes phi on the space E alpha. And this result is established upon by the Ekland variational principle, and we can get that the corresponding function phi is bounded from below. The first case, and then theorem 4.10, if f satisfies the condition H1, H2, and H3, then boundary model problem has at least one non-zero weak solution on ER. And in these conditions, we can find that the functional phi satisfies the mountain path lemma, and the phi has mountain path structure. And so the weak solution can be obtained. And this is the proof details. We will omit it. And finally, we point out that for R between 0 and 1, if U is a weak solution of boundary world problem, then U is also a solution of boundary world problem. And then the problem be solved. And the last section is about fractional differential equations of motion in terms of Reid's fractional derivative. And Dr. Chen has said that in 1931, and Professor Bloch has pointed out that when the equation of motion has the first derivative term, it means the mechanic system is non-conservative, is dispactive. Then the equation of motion can't be derived by the variational principle. And Professor Bloch's work is complicated Anderson's principle, and we have know that Anderson pointed out that most physicists would be not only willing to accept as axiomatic the existence of world as principle, but would be also learned to accept any dynamic equations that were not derivable from such a principle. But unfortunately, if we consider the deceptive mechanic systems, its equation of motion can't be derivable from such principle. So Dr. Chen said, and Professor Bloch's work is a dark cloud. And however, Professor River published 2 articles to solve this problem. And River observed that the second derivative of Euler-Lagrange equation corresponding to the first derivative of the Lagrange in the square So think the first derivative term in the Euler-Lagrange equation, the damping term should corresponding to the half-order derivative. And then we will apply the theory of fractional order calculus, develop the mechanics system of the non-conservative Lagrange mechanics. And in fact, in reverse articles, there are some mistakes, but reverse idea is great. And lately, many authors like Professor Klim and John and me, etc., and give many studies about this. And we will introduce the work of Professor Zhang. And this section also three subsections. Firstly, the properties of Ritz fractional derivative, and secondly, the fractional Lagrange equation, and thirdly, we give an example. And we are familiar with the Riemann-Neumann fractional derivative and the capital fractional derivative. Here is the Ritz fractional derivative. Ritz fractional derivative, you will find that the tau is from A to B, and here is t minus tau and absolute. And this is the Ritz capital fractional derivative. And also integrate from A to B, and here is t minus tau and absolute. Here is the nth derivative of f. Clearly, for R between 0 to 1, the relation between the definitions of Ritz fractional derivative and are either derivative or capital derivative as this. We can derive this relation just from the definition of Ritz fractional derivatives. We had now, and when we establish the variational method for fractional equation, the key formula is integration by parts formulas. And here, for Ritz derivative, the integration by parts formulas also hold. And this is about Ritz derivative, and this is about the Ritz capital derivative. And you can see the details in Agrova's paper, this paper, published at 2007. And then we consider the fractional Lagrange equation, and given action function, give functional I defined as this. TQ first derivative, and then the Ritz fractional derivative. Oh, he is Q. Q. And by the use of Hamilton principle and fractional integration by parts formula, we can conclude the Ritz fractional Euler-Lagrange equation as this. And you will find that here is about Ritz capital fractional derivative, and here is Ritz fractional derivative. It is also a composition. And at last, we give an example. The Lagrange function of non-conservative deceptive Metonic systems be given as this, and the Lagrange function L equal to this M. And here is the raised capital derivatives score. And we combine it in this formula and with 5.6 formula, we can get under this equation. Here is equal to 0, equal to 0. Under this term, we have a family with it, and now we consider the third form. For the third form, we first note that the relation between the capital derivative and the Riemann-Urey derivative as this. And moreover, the composition, this is the half derivative and then half derivative, all from A to T, all are left fractional derivative, then half equal to 1. And for the right derivative, half equal to 1. And generally speaking, this equality is not hard. But if f is the original function of some functions, then the relation hold. And you can refer Semmel's book all the details. Semmel has published a book at 1993. There is details you can see. And combined with the equation 5.2, there we can consider the third term, and raise the capital half fractional derivative, and then raise half derivative, and this. Then we can conclude that they equal to the first derivative of Q. Consequently, the equation here is equal to 0. The equation 5.h be changed as this. This is the classical motion equation. And then we know that the classical motion equation here has a damping. It is said that this equation is non-conservative Metonic systems. This equation is the Euler-Lagrange equation of the functional L. It means that the deceptive Metonic systems can be derived by variational principles. So the dark cloud be solved. And this is just a simple introduce. If some of you want to know the details, you can read the list references. And summary speaking, and order calculus can be used in the conservative mechanical system or deceptive system dynamics modeling, and FOC can solve some difficulty mechanics problem which can't be solved with the classical calculus. And so let us go fractional and Dr. Chen's leading. Thank you for your time and patience.